Hi, my name is Vitor, and in this short video I'll talk about why we have designed a new consensus protocol called Atlas that is specially tailored for planet-scale systems. But first, let's deconstruct the title of our paper. We replicate data for fault tolerance. As an example, consider this case where we have 3 replicas and one user that is accessing the system. If the replica being accessed by this user becomes unavailable, the user can fail over to another replica, and the system remains responsive. And we replicate on a planet scale to minimize latency, which may happen since users can now access the system through the closest replica. With replication comes the question of how consistent is the data being replicated. In this paper, we consider the strongest consistency model, linearizability, in which the system behaves like there's a single copy. The classical way of implementing linearizability is through state machine replication, or SMR. In SMR, the system is defined by a state machine, and there's a protocol that determines the order in which commands are applied to the state machine at each replica, keeping replicas in sync. And the question we set out to answer was, can we attain low latency with planet-scale SMR? And for that we have identified 3 properties. First, in order to process an operation, the protocol should contact small quorums that are nearby. Moreover, the protocol should be leaderless. In leader-based protocols, when the leader fails, the system is unavailable until a new one is elected. Leaderless protocols don't suffer from this problem, as there is no single point of failure. And since any replica can process commands, we also get load balancing. And finally, there are no additional hops to reach the leader, which means that we don't have clients that experience high latency just because they are far away from the leader. The final property says that commands should be processed in a single round trip. Now let's check if existing SMR protocols have these properties or not. Paxos is a leader-based protocol where only f+1 replicas need to be contacted by the leader. However, commands are processed in a single round trip only when the client is collocated with the leader. ePaxos is a leaderless protocol that requires large quorums containing 3/4 of all replicas. In ePaxos, commands are processed in a single round trip only if there are no conflicts, and we say that two commands conflict if, for example, they access the same key in a key-value store. Before talking about Atlas, let me first talk about an experiment that motivated our design decisions. This experiment was run on Google Cloud Platform, where we had each data center periodically pinging the remaining data centers and recording the ping latency. After 3 months, we searched for link slowdowns, where a slowdown would be a ping returning after a few seconds, and we observed that when these slowdowns occurred, they were never incident to more than one data center at a time. Since natural disasters leading to the loss of a data center are rare, and concurrent link slowdowns are also rare, it is not necessary to assume high values for f in a planet-scale scenario. And for this reason, the quorum size in Atlas is a function of f, allowing Atlas to have small quorums for small values of f. This contrasts with ePaxos, in which the system size fully determines the quorum size, resulting in unnecessarily large quorums for large numbers of replicas. Atlas is leaderless and can process most commands in a single round trip, what we call a fast path. And this is possible because Atlas employs a flexible fast path condition that allows the fast path to be taken even when conflicting commands are submitted concurrently. If you're curious, please check the longer version of this talk or the paper for more details. There we show that Atlas recovery mechanism is significantly is significantly simpler than previous protocols. You'll also find many examples, optimizations, and a comprehensive evaluation. We also have an extended version on archive with a proof of correctness. And that's it for this video. Have a nice day.